Hello, welcome to the second day of uh, proving geometric proofs. Now, in this one, I want you to remember all of these different reasons. I'm not going to go through them all right now, but the top few we use a lot in algebra, and we use a little bit with geometric proofs. But segment addition and angle addition, those are really good when we need some values. Um, if we need a longer, if we need to put something, a longer segment in or reference a bigger angle, usually that's a way we can get the bigger angle in. The definitions, we're actually going to do some problems talking about what we can get by the definition of each of these right after this. Vertical angles theorem tells us that vertical angles are congruent. Linear pair theorem says that a linear pair of angles should be supplementary. Complementary theorem says that right angles, these two add up to 90. There's a bunch of right angle theorems. I think there's like 5. And take a look at them. Most of them are talking about when right angles are going to meet at 90. All 4 of these angles would then be 90. Perpendicular lines cross at 90 degrees, things like that. And then supplements theorem adding up to 180. Now this is the thing that is going to go, we're going to talk about the definitions. So if angle 1 and angle 2 are supplementary, what thing can we get out of this? And a conclusion we can get is the measure of angle 1 plus the measure of angle 2 is going to equal 180 degrees. So this is just like one step in a proof. And the reason here would be definition of supplementary. Now, if HJK is congruent to KJM, then we can say JK is an angle bisector, and that's the definition of bisector. Now, if these are perpendicular, then we can say angle ABC, I should say measure of angle ABC equals 90 degrees, and that's just the definition of perpendicular. And for that one, you could also say one of those right angle theorems as well. Now, if we know two angles add up to 90 degrees, then we could say angle 1 is complementary to angle 2, and that's definition of complementary. Now, if we know A is the midpoint of this segment, then we can figure out MA is going to be equal to AN, and we know that this is equal to that because that's the definition of midpoint. Now, if we know those two are a linear pair, then we could say that angle 1 is supplementary to angle 2, and that's the definition of linear pair. And this one could also be the linear pair theorem as well. Both those would be acceptable, the definition and the linear pair theorem. Now, if I know xy bisects this big angle, I could say angle CXY, maybe say measure so we can say equals, is equal to the measure of angle YXD. And that's the definition of bisector. Now, if we know two angles are congruent, only thing we can conclude from that, or equal, I should say, the only thing we can conclude is those things would be congruent to each other, and that's the definition of congruent. if they're complementary, we know that they'll add up to 90 degrees. And that's the definition of complementary. If J is a right angle, then the measure of J is 90 degrees by the definition of right angle. And we have one last one, E is congruent to F. We can show that measure of angle E is equal to the measure of angle F by definition of congruence. All right. Now we have that taken care of, the definitions. So let's try a couple more proofs. So if we have this situation, the first thing we're going to write is all of this for the given statements. So let's just take this, throw it in here. I'm not going to take your time writing that in. Hopefully you can do that. So then if we know this, y is angle 1 plus 1 plus 1, 360. Well, I know these two are equal, so I'll just put 1 in there. And I know those are equal, so I'll put 1 in there. That's by substitution. Now if I know those three add up to 360, I can just add them together. So 3 times the measure of angle 1 is equal to 360. And how I get from this line to this line is I divide on both sides. So that's the division property. All right. That's our first proof. The second proof, we'll start off and say, write all our given information in. So AE is congruent to CE, and AB and AC or CD bisect each other. Now, since that's given, why is AE congruent to EB and CE congruent to ED? Well, if they bisect each other, they're going to cut each other in half. So that's just the definition of bisector. Now, if we know they're congruent, we know they're going to be equal by the definition of congruence. So now if AE equals these, then CE equals ED, and AE equals CE, then CE is going to equal EB by the transitive property. And now if this is the case, symmetric tells us we switch those around. So that would be EB is equal to CE. And now if it's like this, how do we know EB is equal to ED? Well, EB is equal to CE and CE is equal to ED. So the transitive property, again, tells us that that's true. So now we just have to do this last one, which we already always know that's the last thing we write. And why is that true? That's the definition of congruence. All right, let's try. I think we have 2 more. All right, now these last 2, there's nothing written. We just have to try to do them on our own. So the first thing we want to do is write the given information. So AB is congruent to CD, and that's because it's given. Now the other thing we know is the last thing is AC is congruent to BD. So we'll eventually want that. But we know that this is congruent to CD. Now we need an AC in here somewhere. So in order to get AC in here, we have to do some angle addition. So let's do some angle addition. But before we're adding, oh well, sure, we can do this. So we can say AB plus BC is going to equal AC. And BC plus CD is going to equal BD. I'll say DB. And that's given. So now we have an AC and a BD in our equation. So that's pretty good. And since these are congruent, maybe it's good to put those as to an equal sign so we can use those in equations. So then that's the definition uh, of congruence. All right, so now we have this information. We know AB is the same thing as CD. So uh, if I put that into the equation, I could say CD plus BC is equal to AC. And that's just substitution. But now if BC plus CD plus BC equals AC, and that same thing equals DB, then we know AC has to equal DB or BD. And that's substitution or transitive. Now once we know that, we can say they're congruent. And that's just the definition of congruence. All right, we have one more proof we're going to try on our own and then see how you do. All right, easiest thing, write down the given information. All right, so if I know this measure is equal to this measure, and AGC is equal to DGF, um, now we want to prove that 3 and 4 are congruent. So, or measure of angle 3 is equal to angle 4. So now what I would do is I would say we got to put this big angle in here somewhere and get angle 3 in there. So let's say angle 1 plus angle 3 is equal to the big one, angle AGC. And angle 2 plus angle 4 is equal to the angle DGC, or DGF. And that's just the angle addition postulate. All right, so we have those set up. Now, once we have those, uh, since AGC and FGD are there, we can just substitute that in. So we're seeing that measure of angle 1 plus the measure of angle 3 is going to be equal to angle 2 plus angle 4. And that's just substitution. Should have an M in front of these. Just noticing my lack of M's. Otherwise, they're full angles. And now, since measure of angle 1 and measuring angle 2 are the same, instead of writing measure of angle 2, I can just write measure of angle 1. And that's substitution. Now if I subtract the measure of angle 1 on both sides, I'm going to have measure of angle 3 is equal to measure of angle 4, and the reason is subtraction property. All right, hopefully this makes a little bit of sense. This is a long video, but hopefully it clarified something for you. Good luck trying on your